So this is Dr. Russ talking about step 2, describing the comparison distribution, and this is part of the 5 steps of hypothesis testing. So the 5 steps are here. Step 1, parse the problem we worked with last time. Step 2 is describe the comparison distribution, and that's what we're working with today in this lecture. And step 3 is to determine the cutoff point. Step 4 is plotting the z-score. And step 5 is conclude and interpret. So in this chapter, we're comparing a sample of one individual with a group of individuals. And in this example, the individuals will be apples. So the question is this: do apples with a particular fungus rot in fewer days than apples in general? So step 1 is parse the problem. We worked with this last time. Population 1 are apples with a particular fungus. Population 2 are apples in general. The dependent variable, also called DV, is days until rotting, the number of days until apples rot. Tails, one-tailed low, and I get that from the word fewer in the question. And so the research hypothesis, which I've just listed here as H1, population 1 will rot in fewer days than population 2. And the null hypothesis, which I've just written here as HO, population 1 will not rot in fewer days than population 2. So here's that question again. Do apples with a particular fungus rot in fewer days than apples in general? And in order to answer the question, we need to know the number of days it takes to rot for population 1, the apple with a fungus. Right here, that's our sample. And population 2, which is all the other apples, all of those. And all of these other apples make up the comparison group. So the information about population 2, apples in general, all of these, in this case, the number of days it takes to rot, and this is what we look for in step 2. Information about all of these apples in general, which is population 2, and which we'll call the comparison group. So it's what we're comparing our special apple to. So here's the thing. The apples in population 2 are not all going to rot in the same number of days. There's going to be some variability. Some apples will rot rather quickly, like this one, 23 days. Some apples will rot rather slowly, like these 32 days, 36 days. So the comparison distribution is represented by a histogram showing how many days it took each apple to rot. So here are apples, and let's assume we know the days to rot for each of these apples. Well, actually, for our work, we aren't going to solve this problem in this chapter. Previous researchers gathered data about the number of days it takes to rot for typical apples, and they plotted all of those rot days into a histogram. And the characteristics of this histogram, that's what we're describing in step 2. So in this case, you can see frequency on the side y-axis, the number of apples in each category, and the dependent variable, the number of days it takes to rot. And so this is the histogram, and every apple in the entire population, we assume we know the number of days it takes to rot, and it's all plotted into a histogram. And so this is what we're describing. So we have this histogram, and it's based on this theoretical distribution of all of the apples in the population, and so it kind of doesn't look much like a histogram anymore. So after we work with it, we usually just see the shape of the histogram, and we describe this comparison distribution in 3 characteristics, and the first is the shape. And in our class, we're always going to assume that the comparison distribution, that is the number of days to rot for all these apples, that it has a normal shape. And that's what we'll pretty much be writing for shape in the next few weeks. Shape, normal. But we also describe this comparison distribution, the number of days to rot, in terms of its center. And so we would just calculate the center, mu, is 26.5 days to rot. The third way we describe the comparison distribution is through spread. And spread is represented by the standard deviation. And so in this case, sigma is 2.7, and that would tell how far apart the points are from the mean. Greek letters are used for the comparison distribution, like sigma and mu here, because they represent known information from a really large number of individuals. And we don't even know all those individuals. We can't get them back. So this represents a theoretical distribution, or a distribution that has been, the raw data are no longer within our reach. So sigma, lowercase sigma, means standard deviation of a population, in this case population 2, the comparison distribution. And mu, lowercase mu, is the mean of population 2, also referring to the comparison distribution. So in this chapter, you'll find this information in the problem itself. Let's take a look. Our first example is marriage satisfaction. So you might see a problem like this. Do married women who spend 2 or more hours a week with close female friends have greater marriage satisfaction than married women in general? Dr. Sampson suspected that spending time with female friends was important, so she arranged for one of her clients, Sandy, to spend 3 hours each week with people she viewed as close female friends. After a month had passed, Sandy's marital satisfaction was 7.5. The mean marital satisfaction for people in general was mu equals 6.2, and the standard deviation was 0.7. Test this hypothesis using probability of 0.05, alpha 0.05. And you can see here that this key information is stated in the problem. In this example, we do have mu and sigma stated. That's not always the case. And so when it comes to step 2, we would describe this in our 3 ways. We'd say the shape is normal. This is an assumption we'll stay with in this entire class. We'll say the center, mu equals 6.2, and the spread, sigma equals 0.7. A second example. Officer Warren believed that people who viewed videos of car accidents would drive at slower speeds than the general population. They'd clocked data on a particularly dangerous stretch of road for a long time and knew that there was an average speed of 61 miles per hour with a standard deviation of 6. He showed the video, that is, the video of the car accident, to a young man who was helping out in the station, and later found out that his speed on that dangerous section was 52 miles per hour. Test the hypothesis using a probability level of alpha equals 0.01. So here we don't have mu and sigma given, but we can still see in the problem that we have to infer a little bit. They'd clocked data on that road for a long time and knew that there was an average speed of 61 miles per hour with a standard deviation of 6. So we have to dig a little deeper, but there's the information. We know that this 52 miles per hour isn't what we're looking for because this is just the speed of that one young man. So in this problem, the comparison distribution would be described as normal. With the center, we'd write mu equals 61, sigma equals 6. Next example, morning reading. Callan was curious about whether statistics students who studied first thing in the morning had higher quiz scores than statistics students in general. He asked his roommate to study for statistics first thing in the morning, and that roommate got a 92% on the first quiz. The average score for students on this particular quiz was mu equals 76, sigma equals 8. Test Callan's hypothesis using a probability level of alpha equals 0.05. And in this case, we can see we have the population information clearly stated, and so we would finish step 2 like this. Shape normal, center mu equals 76, spread sigma equals 8. And I won't read this example to you, but you can see here that our mu and sigma are stated using the symbols, and we would describe the comparison distribution in this way. So to summarize, the comparison distribution refers to information about population 2 with which we will compare scores in our sample. We describe the comparison distribution with 3 characteristics: the shape, which will be normal in our class, the center, which is the mean of the distribution represented by mu, and the spread, the standard deviation, represented by sigma. And we're always referring to that comparison distribution in step 2, not the sample. Finally, the comparison distribution is represented in Greek letters if it is given or known from a large group of individuals over time. And just a good example of this would be body temperature. It's commonly known, that the average human body temperature is 98.6. But we know some people are higher and some people are lower and different times a day. And, it's not exactly 98.6 for every person at all times. But this is the norm, and it's established from large numbers of individuals over many, many years. We could not possibly go back and get all these individuals. So we would use Greek symbols. Hope this was helpful.